Every single photograph of the sun ever taken in the entire history of human civilization was captured from almost exactly the same angle. Not because scientists never wanted a different view, but because it was, until extraordinarily recently, physically impossible to get one. Every planet, every previous spacecraft, every telescope ever pointed at our star has been confined to roughly the same flat plane, sweeping around the sun's equator, staring straight at its middle like an audience seated entirely in the front row of a theater, with no one ever allowed to see what was happening up in the rafters. In March of 2025, for the first time in human history, that changed. And when scientists finally got their first real look at what has been hiding at the sun's south pole this entire time, what they found was not the calm, orderly structure most models predicted. It was chaos, a jumbled patchwork magnetic field unlike anything ever recorded at either pole of our star. And just months later, a second, entirely separate discovery revealed that whatever is happening down there is moving in ways that violate the sun's own established rules. This is the story of what is actually happening at the bottom of our own star, right now, and why? The scientists studying it keep describing the region in one particular word: terra incognita, unknown territory. To understand why nobody had ever managed this before, you have to understand a basic, almost embarrassingly simple geometric fact about our entire solar system. Earth, along with every other planet and virtually every spacecraft humanity has ever launched, orbits the sun within a flat, disc-shaped region of space called the ecliptic plane. From that vantage point, no matter how powerful the telescope, no matter how close the spacecraft gets, you are always looking at the sun essentially edge-on, catching, at absolute best, a grazing, heavily foreshortened glimpse of its polar regions, never a clear direct view straight down onto either pole. There has been exactly one exception in the history of space exploration. A joint ESA and NASA mission called Ulysses flew over the sun's poles between 1990 and 2009, gathering genuinely valuable data about the space environment up there. But Ulysses carried no cameras at all. It could measure particles and magnetic fields as it passed through the region, but it could never actually show anyone what the sun's poles looked like. For the entire span of human civilization, staring up at the sky, the two most important regions of our own star, and the places where its magnetic behavior actually gets decided, have remained completely, totally invisible to direct observation. The spacecraft that finally solved this problem is called Solar Orbiter, a mission led by the European Space Agency with significant contributions from NASA, launched in February of 2020. For its first several years in operation, Solar Orbiter behaved much like every other sun-observing mission before it, orbiting within that same familiar ecliptic plane, gathering valuable but fundamentally limited data. Then, in February of 2025, it began what mission scientists have described as the true beginning of its primary purpose, deliberately tilting its orbital path out of the ecliptic plane entirely, climbing to an angle of 17 degrees below the sun's equator, roughly 2.5 times steeper than any previous sun-observing spacecraft had ever managed, on March 16th and 17th of 2025. At that new, steeply tilted angle, Solar Orbiter turned 3 of its most sophisticated instruments directly toward the sun's south pole and captured something no human being had ever seen before: a direct, clear image of the actual pole of our own star. Carol Mundell, ESA's Director of Science, described the moment in terms that reflected exactly how significant this achievement genuinely was, stating plainly that this marked humankind's first ever view of the sun's pole. The 3 instruments involved each captured a different piece of the picture. The polarimetric and helioseismic imager, led by a team at the Max Planck Institute in Germany and headed by principal investigator Sami Solanki, photographed the sun's visible surface in ordinary light, while simultaneously mapping the direction and strength of its magnetic field. The extreme ultraviolet imager captured the sun's outer atmosphere glowing in wavelengths invisible to human eyes, and the spectral imaging of the coronal environment instrument tracked the actual movement and temperature of solar material by measuring the specific light emitted by different chemical elements, hydrogen, carbon, oxygen, neon, and magnesium, as they streamed across the polar surface. Sami Solanki, describing the team's mindset heading into this genuinely unprecedented observation, put it about as honestly as any scientist could. He said plainly that they did not know exactly what to expect, because the sun's poles were, in his own words, literally terra incognita, unmapped territory in the truest possible sense. What they found immediately upended one of the more basic assumptions scientists had long held about how the sun's magnetic field is supposed to behave. Under normal stable conditions, each of the sun's magnetic poles carries a single dominant consistent polarity, functioning conceptually similar to Earth's own north and south magnetic poles, each one cleanly one type or the other. What Solar Orbiter's PHI instrument actually detected at the South Pole was nothing like that clean, orderly picture. Instead of a single dominant polarity, the magnetic field maps revealed patches of both positive and negative polarity mixed together within the same polar region simultaneously, a genuinely jumbled, disorganized magnetic structure that stood in direct contrast to what a stable pole is supposed to look like. Coverage of the discovery described the resulting picture using words like messy and turbulent, language that mission scientists themselves did not dispute. The explanation for why this chaotic mess exists is, on its own, a genuinely fascinating piece of solar science. Even before you get to the parts, scientists still cannot fully explain. The sun runs on an internal magnetic rhythm lasting roughly 11 years, cycling between a quiet phase of low magnetic activity and a violent phase of intense solar flares and eruptions called solar maximum. At the peak of that violent phase, something remarkable happens. The sun's entire magnetic field flips, its north and south magnetic poles essentially swapping places, a phenomenon confirmed to occur but whose precise underlying mechanism remains, even today, only partially understood by solar physicists. Solar Orbiter happened to arrive at the South Pole at almost exactly the moment this flip was actively underway, catching the sun's magnetic field in the messy, a disorganized middle of the process, rather than settled into either of its two stable single polarity configurations. In a sense, scientists got remarkably fortunate timing, capturing humanity's first ever direct image of a solar pole during precisely the brief, chaotic window when that pole's magnetic identity itself was still being actively decided. That alone would have been an extraordinary result, resolving one genuine mystery while confirming, with direct visual evidence for the first time, a process scientists had previously only inferred indirectly. But the story did not end there, and what came next, published 7 months later in November of 2025, revealed something considerably harder to explain away as simply an expected consequence of unlucky timing. A research team led by Lakshmi Pradeep Chitta at the Max Planck Institute for Solar System. Research went back through the detailed data captured by Solar Orbiter's PHI and EUI instruments during that same March 2025 observation window, this time focusing specifically on structures, called supergranules. Enormous cells of hot, churning plasma, each roughly 2 to 3 times the size of Earth itself, that blanket the sun's entire surface. These supergranules function as a kind of conveyor belt for the sun's magnetic field. As plasma flows horizontally across the surface of each cell, it physically drags magnetic field lines along with it, sweeping them toward the cell's edges and building up the dense, web-like network of concentrated magnetic field that structures the sun's entire surface. Scientists have understood this basic mechanism for years at lower solar latitudes, closer to the equator, but nobody had ever been able to properly measure how it actually behaves right at the pole itself, because nobody had ever had a clear enough view to check. What Chitta's team found, once they finally had that clear polar view to examine, genuinely surprised them. The supergranules at the South Pole, and the magnetic field being dragged along with them, were drifting toward the pole at a rate of roughly 10 to 20 meters per second, moving almost as fast as similar magnetic structures found at much lower solar latitudes, far closer to the equator. That result runs directly counter to what earlier research, based entirely on the limited, grazing observations available from the ecliptic plane, had predicted. Those earlier studies consistently suggested the poleward drift of magnetic material should slow down considerably as it approaches the pole itself, arriving in a comparatively gentle, gradual trickle rather than maintaining anything close to its original speed the entire way there. Solar Orbiter's direct measurement showed something else happening entirely. Magnetic material moving toward the pole at a pace far closer to its full equatorial speed than anyone had modeled, with no clear explanation yet for why that slowdown, expected by every prior model, simply is not showing up in the actual data. This matters far beyond simply correcting one specific numerical prediction, because these poleward flows of magnetic material sit at the very heart of how the sun's entire 11-year magnetic cycle actually operates. Picture 2 enormous, invisible conveyor belts of plasma, one in each solar hemisphere, endlessly cycling material between the equator and the poles. Near the surface, this circulation carries magnetic field lines away from the equator and toward the poles. Deep within the sun's interior, in a return loop scientists cannot directly observe at all, that same material is believed to flow back toward the equator again, completing the circuit and, in the process, generating and regenerating the sun's entire global magnetic field cycle after cycle. Solanki, speaking about why this specific region of the sun has remained so stubbornly difficult to understand, put the core problem plainly. To understand the sun's magnetic cycle, he explained, scientists still lack knowledge of exactly what happens at the sun's poles, because that region has simply never been directly observable before now. Chitta described the significance of the new supergranule measurements in similarly direct terms, explaining that these plasma cells function as a kind of tracer, making the polar component of the Sun's global 11-year circulation visible for the very first time in the history of solar physics to anyone actually trying to measure it. It is important, at this point, to be precise about exactly what remains genuinely unresolved here, rather than let this discovery drift into more dramatic territory than the actual science currently supports. Researchers have been direct in stating that this entire result represents a single brief snapshot, just over a week, of continuous observation captured during one specific moment of the Sun's 11-year cycle, rather than a complete, settled picture of how the poles behave across the cycle's full duration. Whether this unexpectedly fast poleward migration holds steady throughout the Sun's entire magnetic cycle, or whether it changes meaningfully as the Sun moves from its current chaotic, flipping state back toward calmer, more stable conditions, is a question that simply cannot be answered yet, and the scientists involved are saying so plainly rather than overstating a single data point into a sweeping new theory. What is genuinely, verifiably true, confirmed directly rather than inferred from a distance for the first time in the history of astronomy, is that the Sun's south pole right now is caught in a state of magnetic upheaval, exhibiting behavior that runs directly against what every model built from decades of grazing, ecliptic plane observations, had confidently predicted it should be doing. And Solar Orbiter is nowhere near finished with this investigation. The mission's tilted orbit is designed to steepen progressively over the coming years, climbing to a 24-degree inclination by the end of this year, 2026, and eventually reaching a full 33-degree tilt by 2029. Granting scientists an increasingly complete, increasingly direct view of both solar poles as the mission continues. Daniel Miller, ESA's Solar Orbiter project scientist, described the March 2025 observations as merely the first step of what he called the spacecraft's stairway to heaven, explaining that in the coming years, the spacecraft will climb progressively further out of the ecliptic plane, delivering ever clearer, ever more complete views of the Sun's polar regions with each successive orbit. Data from the mission's very first full pole-to-pole orbit, which began in February of 2025, did not even finish arriving back at Earth until October of that same year, meaning scientists are, right now in 2026, still actively working through a substantial backlog of genuinely unprecedented polar observations that nobody has ever had access to before. So here is the honest, complete picture of exactly what is actually happening at the bottom of our own Sun right now, laid out plainly rather than sensationalized. For the entire history of human civilization, the poles of our nearest star have remained completely hidden from direct view, and the first time anyone finally managed to look, what they found was a magnetic field caught in genuine disarray, a chaotic mixture of opposing polarities captured mid-flip during the Sun's violent 11-year cycle, and magnetic material sweeping toward the pole at speeds that directly contradict what decades of indirect modeling had confidently predicted. Nothing about this involves broken physics, and no scientist studying the data is claiming otherwise. What it genuinely represents is something science experiences far too rarely, an entire previously unreachable region of a well-studied object suddenly becoming observable for the very first time, and immediately handing researchers a result that does not match the picture they had spent decades building from an incomplete vantage point. Our own Sun, sitting 93 million miles away, studied by professional astronomers for centuries, photographed more times than any other object in the sky, still has an entire hemisphere of behavior that nobody had ever actually seen until March of 2025. And what that first look revealed suggests the mechanism driving our star's fundamental 11-year rhythm, the same rhythm that governs solar flares, space weather, and the northern lights dancing over Earth's own poles, is working in ways considerably stranger and considerably less understood than anyone confidently believed just 2 years ago. If you want to see what Solar Orbiter finds as it climbs even higher above the Sun's poles in the years ahead, subscribe and turn on notifications. Because mission scientists have already said this is only the very first step of a much longer climb, and the poles of our own star are only just beginning to reveal what they have been hiding.